Welcome to another episode of Two Chairs, One Technology. Once again, I'm joined by Andreas Roessler, Technology Manager at Rohde&Schwarz. Andreas, in a recent episode, we discussed the spectrum crunch and what network operators were going to do about that. What do you think is going to happen in the near and short term?
Yeah, that's a good question. Beside the individual strategies of all network operators that we have in the United States, also the US government has reacted to the situation and unveiled the so-called National Broadband Plan. It was unveiled by the Federal Communications Commission, so the FCC. And the initial target was, or is, to free up additional spectrum of 300 megahertz up to 2015. And up to 2020, the plan is to even free up to 500 megahertz of additional spectrum for mobile broadband application. So the FCC targets spectrum between 225 and 4.4 gigahertz. This includes 120 megahertz of spectrum so far being used for analog TV broadcast. And this is what this recent news shown here is all about. As highlighted, the news announces the upcoming availability of additional spectrum at 600 megahertz, where the FCC plans to implement 6 megahertz of guard bands to protect remaining broadcast services. But spectrum at 600 megahertz is not the only candidate. The table to the left shows the identified spectrum that could be made available for mobile broadband applications as it is shown in the National Broadband Plan. In the near and midterm, the FCC explores the possibilities to auction the following frequency bands. As listed, the spectrum is currently used by other communication systems, for instance, military applications. But especially the later frequency bands look promising as they would free up immediately a total bandwidth of 350 megahertz. So with that, the 4.2 up to 4.4 megahertz of spectrum are becoming really interesting. Of course, there are still a lot of regulatory hurdles to take before the spectrum becomes available to any US service providers and could be used, for instance, for LTE or LTE-Advanced. And even then, the third generation partnership project, short 3GPP, and the standardization body behind LTE needs to start its work defining performance requirements, setting limits, while applying regulatory requirements and such. Nevertheless, it is important for today's design engineers to be sure that its test and measurement solution, for instance for handset and chipset development, is future-proof and does support these frequency ranges. And that's the case for the Rohde&Schwarz CMW500 wideband radio communication tester. The unit supports initially a frequency range up to 3.3 gigahertz, but can be easily extended to 6 gigahertz. I got such a unit here, and I will be using a Rohde&Schwarz SMPV100A vector signal generator to generate an LTE uplink signal at 4.2 gigahertz. So we see the MMI here, and what I'm going to use, first of all, I set the frequency 4.2 gigahertz, and I will be using also a power level of 0 dBm as a reference level here. So we will go now into the diagram, and what you see here on the right hand side is the baseband functionality, where I go in and pick the LTE standard. So you see here LTE gives me a couple of choices. What I want to do, I want to switch and using the uplink portion of it, and I will just keep it that way using the default settings and switch that signal on. And you see we have the IQ modulation here, and the only thing I need to do in order to get it on 4.2 gigahertz, switch on the RF. So now my signal is ready. Now over to the CMW500 to configure the instrument to take the measurements. So we need to activate the measurement functionality. I do that here real quick by hitting the measurement button on the front panel. You see here LTE TX measurements becomes available. I go into that and I start the configuration by using the bottom at the right. You see that here. I need to set the frequency to 4.2 gigahertz. I also would like to set the power level 0 dBm. If you remember the setting on the 6th gen, that gave me a peak envelope power of 6.38 dB, which means I have a crest factor and should set a user margin here of 7 dB. And the trigger is also important. I will set it here to free run as this. And what else we need to do? Of course, I'm sorry, we need to set the right bandwidth that we're expecting. The default is 10 megahertz, which I'm generating on the SMPV. So that should be it. We just go in here, switch the measurement on, and here we're going to see we are measuring already the signal at 4.2 gigahertz. So my instrument is capable of doing it. We see the measurement, signal quality here with the EVM, the error vector magnitude. And let's focus on a specific measurement for LTE, in-band emission. I just can click that, double click that here and go into the details. So what you basically see is we are transmitting with 10 resource blocks on a 10 resource blocks of spectrum and using an offset of 2 resource blocks. Here are the 2 resource block offset. This is my 10 resource block transmission. And just to show that we have certain capabilities here of analyzing impaired signals, I will add some IQ impairments here on the signal generator, which you can't see right now. I will just switch them off and add a gain imbalance of 0.25 dB. And as soon as I did that and activated, you see the IQ image becomes available. And in a real device, RFIC for instance, it would show me that my IQ modulator got certain problems. So with that, the instrument functionality quickly shown here, just that we support already today frequencies up to 6 gigahertz with an example of 4.2 gigahertz. That is interesting spectrum that may become available or made available by the FCC to be used or auctioned to US service providers to be used for LTE as a mobile broadband service. Back to you, Chris.
Andreas, that's a great explanation. Thanks. And don't miss the next episode of Two Chairs, One Technology, where we continue to explore other interesting aspects of LTE and LTE Advanced.